All right, buckle up. In the next few minutes, we're going to go on an absolutely epic journey. We're talking 13.8 billion years of history, from the single point that started literally everything all the way to the star that makes our world possible. So let's just start with the biggest question there is, right? How did any of this even get here? The stars, the galaxies, you, me. I mean, where did it all begin? It all started right here, 13.8 billion years ago. But you know, the common image of some kind of cosmic explosion, well, it's a little misleading. The Big Bang wasn't an explosion in space. It was the rapid expansion of space itself, from a single, unbelievably hot and dense point. So, let's take a closer look at our universe's grand opening ceremony. This timeline, it really breaks down those first chaotic moments. It starts with the singularity. Then, bam, it goes into inflation, an expansion that was literally faster than the speed of light. Right after that, nucleosynthesis cooked up the first atoms, hydrogen and helium. But the key moment for us, the really cool part, is recombination. This is when the universe finally cooled down enough to become transparent, releasing this incredible flash of light that we can still detect today. We call it the cosmic microwave background. And from there, gravity started its slow, patient work, pulling all that matter together to build the first stars and galaxies. So that's how it all started. But what is all this stuff, really? This whole cosmic web of galaxies? What's it actually made of? The answer, well, it's mostly a complete and total mystery. Okay, get ready for this. Take a look at this chart. Everything we know, every star, every planet, every galaxy we can possibly see, all of it adds up to just 5% of the universe. Just 5%. The rest, a huge 27%, is something we call dark matter. We can't see it, but we know it's there because its gravity is like the invisible glue holding entire galaxies together. And then, an even bigger chunk, 68%, is dark energy, some mysterious force that's actually pushing the universe to expand faster and faster. It's pretty humbling when you think about it, isn't it? Now, let's zoom back in on that tiny 5% of ordinary matter, because that's where we live, that's where the magic happens. We're moving on to the life and death of stars, the cosmic forges that created the very elements for life itself. What we're looking at here is the entire life story of stars, from their birth in these gorgeous nebulas to their spectacular, explosive ends. And the wild part is that it all boils down to just one single factor: its mass. How much stuff a star starts with dictates everything that's going to happen to it. This table makes those cosmic paths a lot simpler to follow. You've got your low to medium mass stars, like our own sun. They'll eventually puff up into a red giant and then just fade away, leaving behind a super dense core called a white dwarf. But the high mass stars, ooh, they go out with a serious bang. They become red supergiants, then explode in a supernova, leaving behind a neutron star. And the absolute most massive stars, their supernova is so powerful that their core collapses into one of the most bizarre objects in the entire universe, a black hole. And just to give you a sense of how extreme these things are, get this. A single, tiny, sugar cube-sized piece of a neutron star would weigh about 1 billion tons here on Earth. That's like taking the entire human population and squishing it into a space you could hold in your hand. The density is it's staggering. And then we have black holes, the final stop for the biggest of the big stars. Right at its heart, you've got the singularity, a point of infinite density. Then around that, the photon sphere, where light literally gets trapped in orbit. And of course, the most famous part is that outer boundary you see, the event horizon. The event horizon truly is the point of no return, but it's not a physical surface you could, touch. It's an invisible boundary in the very fabric of space and time, what we call space-time. The second anything crosses it, even light, gravity's pull becomes absolute. There is no getting out. For centuries, we've studied the cosmos just by looking, but now we're learning to listen. So let's talk about these incredible ripples in space-time and how we're actually hearing the universe's most dramatic events. This slide shows what happens when truly gigantic objects, like two black holes, spiral into each other and collide. The impact is so violent it creates gravitational waves, and these are literal ripples in the fabric of space-time, spreading out across the universe just like the ripples on a pond. And this incredible machine is how we detect them. It's called LIGO, and it's not a telescope, it's more like a cosmic antenna. As a gravitational wave passes through Earth, it momentarily stretches one of LIGO's long arms and squeezes the other by an impossibly small amount. We're talking less than the width of a proton. By using these hypersensitive lasers, LIGO can measure that tiny distortion, letting us hear the echoes of cosmic collisions from billions of light years away. It's amazing! All right, after that trip through the depths of space, let's bring it all back home. It's time to meet our very own neighborhood star, the Sun. So, on the left, you see the inner workings of our Sun, from the nuclear furnace in its core all the way out through its different layers. And on the right, you see how all that inner turmoil actually shows up on its visible surface. Those dark patches, those are sunspots, and they're a direct result of the intense magnetic storm that's churning deep inside. So what exactly are these sunspots? Well, they're cooler, darker areas on the sun's surface, and they're driven by these really powerful magnetic fields. Their numbers go up and down in a roughly 11-year cycle. And here's why they matter to us. The more sunspots we see, the more magnetically active the sun is, and that means a much higher chance of powerful solar storms being thrown our way. Now, solar storms come in two main flavors. Over on the left, you see a solar flare. That's an intense, sudden burst of light and radiation. And on the right is a coronal mass ejection, or a CME. That's a much larger eruption, a massive cloud of solar plasma getting hurled out into space. Let's just quickly break down the difference, because it really does matter for us here on Earth. A solar flare is a flash of pure radiation. It travels at the speed of light, so it hits us in just about 8 minutes. And it's the kind of thing that can disrupt radio communications. A CME, on the other hand, is a physical cloud of charged particles. It's slower, taking 1 to 3 days to get here, but its impact can be way more severe. It has the potential to damage our power grids and even knock out satellites. So we've gone from the Big Bang to the life and death of stars all the way to our own sun. And here's the most amazing part of this whole story. The very elements that make up our planet and our bodies, the calcium in our bones, the iron in our blood, all of it was forged in the heart of a massive star that lived and died billions of years ago. We are quite literally made of stardust. Our cosmic journey started with a single point of light 13.8 billion years ago. Today, we're not just seeing the universe, we are hearing its most ancient and violent events through gravitational waves. So the real question is, with these new senses, what profound secrets are we going to uncover next?